So we had a lecture on Monday. That lecture, those things on that lecture will be on the next exam, right? So that's why that stuff wasn't on this exam, the phase diagrams and stuff, right? And so the phase diagrams actually go straight into this, the properties of solutions. And this is going to be a big thing because the next few chapters we do is going to be about solutions and concentrations and stuff like that, right? And it's going to get a little bit more math heavy. Not today, but it will get more math heavy soon. Okay. Um, and I noticed as I was teaching, not you guys, but throughout the years, that the difficult thing for most students in chemistry is connecting the math with the chemistry. And so we're going to work really hard on trying to get that, hammered home. Okay. So let me get my laser out. Let me get my laser out. All right, so solutions, what are they? Solutions are homogeneous mixtures of two or more pure substances. And so when you have a solution, right, the solute is dispersed uniformly throughout the solvent. So a good example of that is salt water, right? You have some salt water, and what's in there is water, of course, and the salt is dissolved in the water, okay? So in that example then, the solute, right, is what? The salt, okay? And then the solvent is the water. So you'll hear me say this a lot where I say water is a universal solvent because water can solvate a lot of different things, okay? Water can solvate a lot of different things. And so we call it the universal solvent. So the ability of substances to form solutions depends on a couple different things. Its natural tendency toward mixing, right? So that's the thing I was talking about last time on Monday about how you put oil and water together, do they have a natural tendency to mix? No, right? So it has to have a natural tendency to mix, right? And then also the intermolecular forces, okay? The intermolecular forces. So your first question, go ahead and scan. Let's see how everybody's doing on that question. Where am I at here? True statement. Responses. Okay, so I expected this to be half and half, and it was half and half. And part of the reason why it's half and half is because I forgot to put a word in the question. It should be which of the following is not true about the solutions, right? Sorry, I forgot to put a word in the question. So, uh, this is also an exercise in reading the thing, reading the thing very carefully and also writing the thing very carefully. But notice here I've changed this to say depends on separating and intramolecular forces, right? It should be towards coming together and intermolecular forces. So had I put in the not, it should have been the answer was C. But since it's about true solutions here, I forgot to put the not. A would have been better, right? So I won't even count that for house points this time since I messed up that question by typoing and not putting not in there, right? But that being said, right, tendency toward mixing, right, and intermolecular forces. Remember I said before that intra is inside of molecule and an inter is between molecules. So when you're solvating things, it's always going to be an intermolecular force and a tendency toward mixing, right? So um, both A and B are true, by the way, right? Both A and B are true. The only thing that was not true was C, And I definitely forgot to put the not there. My apologies. Okay, well, I won't count that one towards the house points since I messed that question up. All right, so natural tendency toward mixing, right? We were just talking about that. The mixing of gases is spontaneous, right? Does anybody remember what spontaneous is? Right? Spontaneous means that it happens on its own, okay? Just like it sounds, it happens spontaneously. There are some things that are not spontaneous, right? They're called non-spontaneous processes. And in non-spontaneous processes, you have to do things like add heat to it, do some kind of thing to make it work, right? But for gases mixing with each other, right, it's pretty spontaneous. It makes sense because in the air that we breathe right now, it's 75% nitrogen, 25% oxygen, right? It's 75% nitrogen, 25% oxygen. You think it would be a good idea if we had 100% oxygen since we breathe we breathe oxygen? Probably not, right? Because oxygen is super flammable, right? And if you were to light a match or something, it just explode in your face, right? So that's a good thing that the air that we breathe is 75% nitrogen, which is pretty inert, N2, and then oxygen is only 25%. Okay, but there was a time though, back in the day, right, where there was a lot more oxygen in the atmosphere. Sorry, a lot more carbon dioxide in the atmosphere, and and so, and then, so let me say that one more time. Back in the day, there was a lot more oxygen in the atmosphere, right? And so what would happen is you'd get these huge animals, right? Like, big insects and stuff, right? If you didn't know this, back at like during like the Carboniferous period or so, there was there were huge dragonflies and huge insects. And the way that insects breathe, they don't have lungs like we do, right? They have actually little holes in their exoskeleton that they breathe out of, right? So we breathe through our mouth and nose and we inhale, but they actually exchange air straight from the air through holes that are in their exoskeleton. And so, since they were able to do that, the more oxygen there was, the bigger they were able to grow, the more healthy they were. And but see now we don't see huge bugs like the size of my chest anymore, right? They were dragonflies like as big as like a bird, right? But they don't exist anymore because our atmosphere has changed, right? Where the most efficient way to actually breathe in oxygen is to breathe in through your nose, right? And your mouth, and insects don't do that. And so now the insects are super small, right? Most insects anyway are super small. So so that happened back in the day, back when we had really big, things like that. That's why you have animals back then that are like dinosaurs that are like huge, right? Yeah, yeah, exactly, exactly. I mean, there were small insects back then too, but a lot of them got really big because there was so much more oxygen in the atmosphere. But the thing about it was, it wasn't a big deal because these animals weren't like, sparking, fires, right? So it wasn't going to explode in their faces. So it's really funny in that way. Anyway, so um, does anybody know the reason why there was so much oxygen in the atmosphere back then? Well, it's because we weren't cutting down plants, right? Plants were breathing in CO2, right? And they were breathing out a bunch of oxygen, right? And so since there were so many plants, and not to mention there's a lot of microorganisms in the ocean too that make oxygen, mostly dinoflagellates, algae, that kind of thing, phytoplankton. They all are plant-like. They use chlorophyll, and so they will breathe in CO2, expend out oxygen, and so there was tons of oxygen in the atmosphere. But so it's a good thing since us humans like to burn things down, right? That we don't have that much oxygen in the atmosphere. So when mixing, okay, each gas acts as if it's in its each gas acts as if it is alone to fill the container, right? So mixing causes more randomness and the position of the molecules, increasing the thermodynamic quality. It's called entropy. So entropy is the way I remember it. Just remember it like this: entropy is disorder. Okay, so the more entropy you have, the more disorder there is, right? And you can see how gases are very disordered because they're just flying all over the place, right? They're just, bouncing. That's how you have a balloon, right? Because they fill up everywhere and they're just bouncing all over the place. So that's more disordered. And then as you do things like bring the gas to condense to water, it flows like a liquid, for example. It's less disordered now. It's more ordered. It's flowing, and you can control where water goes, right? You can't control where air goes. And then you get super ordered, right, after you freeze the water into ice, right? So there's even less entropy there, right? And we saw that structure of water with the hydrogen bonding looking like crystals, right? And that's highly ordered. Things that are solid are highly ordered, right? There's not much entropy. So gases, they have a lot of entropy. They're very disordered, right? The formation of solutions is favored by the increase of entropy that accompanies mixing. So here we have two gases. It's oxygen gas and argon gas right here. And then they mix together and they become a mixture, right? A mixture of argon and oxygen, okay? If you didn't know this, actually, that they, and you know how you feel when you open up a chip bag, right? Even though you seal the bag of chips as best as you can, they seem to go stale. But if you keep it sealed all the time and never open it, like, 2 months later, they still feel fresh, right? And the reason why is because when they're filling up the chip bag, they actually evacuate all the oxygen from the bag and fill it up with argon gas. Because it's actually oxygen that actually makes your food go stale, right? Makes bread go stale, makes your food go stale, makes chips go stale, bread go stale, all that stuff, right? So that's actually why food lasts longer when it comes straight from the factory, because they actually evacuate out all the oxygen and put it in like a noble gas, and it's not going to interact with your food molecules, and that's why it doesn't go bad, right? You can do the same thing too if you do like vacuum sealing, but the problem is if you vacuum seal some chips, it's just going to crush the chips, and what's the point of eating those anymore, right? So you can, but so again, we were talking about intermolecular forces in the last episode of Gen Chem 2. And so we have our dispersion forces. This is a review right here, right? We have our dispersion forces, heptane and pentane here. They disperse from each other, right? Why? Because they're both hydrocarbons, both made of mostly hydrogen and carbon, right? And they're also nonpolar, okay? So when they do that, they're similar in shape, they're similar in size, right? Similar in chemical composition. So they're going to do what? They're going to disperse, right? They're going to do dispersion. Okay? Then we have our dipole, right? Where we have two molecules here, one of acetone and one of chloroform here, right? And then this is just a natural, uh, positive and negative charge that's on the molecule just from the atoms that are in it. So here we have acetone, where acetone on this side is carbon and hydrogens, and then on the other side is oxygen, right? So you've got a super electronegative on this side, pretty much partial positive on this side, so that automatically makes a dipole, all right? One side's positive, one side's negative, and then you have chloroform, does the same thing too. One side's got a carbon on it, but the other three on the other side have what? Three chlorines, also super electronegative, right? And so they do dipole-dipole, okay? Remember, the difference between dispersion and dipole-dipole is that in dispersion, it's usually just CHs, right? Just CHs, okay? And then also, it may have confused you a little bit because the question in the exam said something about London dispersion, right? Instead of just dispersion. London dispersion is dispersion, okay? And that was actually in the notes where I said that dispersion forces are London dispersion forces, okay? Then hydrogen bonding, of course, right? Here we have ethanol. So what it's actually showing you here is that these guys can dissolve each other. These guys can also dissolve each other because of their interaction. And then hydrogen bonding also happens in ethanol too. We talked about this on Monday, right? Where there's an OH here and it likes to hydrogen bond with the water, right? You have to have an electronegative atom with a lone pair on it, right? And some hydrogen to do hydrogen bonding. And then the last one was ion dipole, where we have water, the negative part of water, partial negative part of water, which is the oxygen solvating sodium by surrounding it, right? Because sodium is positive. All of these are interactions that will occur during solvation, right? When you're making a solvent, not making a solvent, making a solution, okay? So attractions involved when forming a solution, right? We have the solute interactions, right? Must overcome the dispersion of these particles to make a solution. So solute is basically having two salt molecules coming together, right? Because remember, the thing that gets dissolved is called the solute, right? Then we have the solvent-solvent interactions, right? Which is two different solvents. And then, sorry, not two different solvents, two different molecules in a solvent, right? And then the solvent-solute interactions occur as particles mix, okay? So solute-solute is two of the solutes interacting together. Solvent-solvent is two molecules of solvent, like water, interacting with each other. And then solute-solvent, solvent-solute interactions is them mixing. So we already have the tendency, for example, salt molecules to want to be together. That's why they form a salt crystal, right? Right? Sodium chloride crystal, they form a salt crystal. And then we also have the tendency for water to stick together, right? Because of hydrogen bonding, correct? Okay. So for something to dissolve, right, the solute-solvent interaction has to be stronger than the other two. Does that make sense? Right? You have to overcome the amount of energy, or you have to overcome the interaction of them wanting to be together, right, for you to be able to get something to dissolve. You have to overcome water breaking, right, the water's tendency to be together, and you have to overcome the salt molecules wanting to be together. And how do you do that, right? In this case, for salt water, it's the ion dipole. Sorry, ion dipole. Is that what I said? I lost my train of thought for a second there. Yeah, ion dipole. The ion dipole interaction between water and salt is stronger than the hydrogen bonding of water to itself, and stronger than the ionic bonding that's happening between um, salt molecules, right? Does that make sense? Okay, I see lost faces.
So how are we going to know if it's not going to be strong
Huh?
enough?
Say that again?
How are we going to know if it's not going to be strong enough? So
We'll get to that part in a second, right? Oh, well, I actually even said it last time already. Remember I was talking about like? Things that are like each other will dissolve each other better because they can overcome those things, those tendencies for them to be with themselves better than, being separated. Okay, so does that make sense to everybody, right? Because I'll say it one more time because I don't hear anybody saying anything. Water likes to stick together, right, because of hydrogen bonding, and then sodium chloride and salt likes to stick together because of ionic bonding, right? But then water comes in, right? And the interaction between water trying to surround the sodium ions and trying to surround the chloride ions is stronger than the ionic bonding, right? And stronger than the hydrogen bonding. Then that's why you can dissolve salt into water. Does that make sense? Right? Okay. That's how they mix, right? All right, so what interactions are involved in forming a solution? Okay, this one was written correctly. Is it asking you to log in every time again? Who was doing that? Oh, Hannah was doing that. She's not even here right now. Huh? Oh. Huh. To me, the network's slow today. I already forgot which one we're on right now. Oh, solution interactions. There it is. Got 4 people. Got 4 people so far. 5 people. There are only 10 of us in here today, right? Or 9? 9 of us. Six people so far. You having trouble, Daniel? It's not scanning? One more person. Did it work? What was it saying? It's just not scanning? Did you scan the first one? Try it one more time. If not, we'll just move on. You did the first one already, so. Okay. Well, this is the distribution right here. So basically a half and half type of thing again, right? Definitely the answer here though, not tricking you at all, right? Is that the answer is D. All these have an interaction. All these do, right? So solute interactions, solvent interactions, and solute interactions, right? That was basically from the previous slide, right? So all these have uh, a are involved. Okay, all these are involved. You're trying to overcome those top two, right? And then you're trying to overcome those top two with this one, right? So that's definitely an all of the above. So let's take a look at this in the in picture way, right? So here we have a saltwater crystal, right? Here we have here we have salt water, and we have a salt crystal in water, right? And right now the salt crystals together, right? The ionic bonds are keeping the salt crystals together, right? The ionic interactions are keeping the salt crystals together, and then there's water, all molecules all around it, right? And then as you start to mix them together, you can speed this up by stirring, right? Or you can just leave it there. It'll eventually do it, right? And you can start seeing how some of these water molecules right here are breaking away from their hydrogen bonding and starting to surround the individual chloride and sodium atoms, right? Does that make sense? Okay. So this is a spot where they're overcoming the the tendency for them to stick as salt molecules and the tendency of them to stick as water molecules together to become this hydrated chloride ion, right? And this hydrated sodium ion, right? With water surrounding it. Okay. Notice that these guys aren't hydrogen bonding anymore, are they? Right? Does that make sense? Notice that they're not hydrogen bonding anymore. Notice that over here, these guys are not hydrogen bonding anymore either. And then eventually you'll get all of them dissolved, right? You'll get all of them. You okay? Okay. Eventually you'll get them all dissolved, right? And they're all going to be in a solution, right? They're all going to be in solution. So this slide here just basically shows you in pictures what I was talking about on that slide. Does that make sense? Right? You start out with them wanting to, these two molecules, water molecules and salt molecules, wanting to stick together. You introduce some mixing in there, and now they're going to start breaking apart their individual hydrogen bonds with the water or their individual ionic interactions with the salt, and then they'll break apart, and then they'll get surrounded by water, right? Of course, there's still hydrogen bonding happening around it because you'll never get it. You'll never, well, you could, but when you're adding salt to water, you always have a whole lot more salt than you do water, right? So there's a bunch of water molecules around that are still doing hydrogen bonding. That's why you still have water, right? But the salt inside is still being separated into its individual components by the water molecules. Okay. So this brings us to the energetics of excuse me, of solute formation, right? So for an endothermic reaction to occur, the enthalpy of mixture must be close to the sum of the solute and the solvent. Slovent? I don't know what that is. Anyway, close to the sum of the enthalpy of solute and the enthalpy of solvent, right? So entropy again will matter. The disorder will matter, right? Depending on what solution is, other solutions are more disordered than some other solutions, right? And the thing I really want you to get from this slide here is that exothermic solutions are spontaneous. Okay, exothermic solutions are spontaneous. And spontaneous means that you're going to have a negative delta H, right? So those are the three things I need you to remember about the word exothermic. Okay, exothermic means it's going to be spontaneous, and then also the delta H will be negative. Okay, the delta H will be negative. Excuse me. So you notice that over here, it's an exothermic process, right? And the number is below zero right here, so it's negative. And then in an endothermic process, right, it's above zero, and so that's positive, right? So if I'm telling you that an exothermic process is spontaneous and it's got a negative delta H, then what does an endothermic process have? Positive and what? Non-spontaneous, correct? Right? Write that down, that's important. All right, so this is something really cool that I wanted to do in class today, but they wouldn't let me because they thought it was too dangerous. There's so many things that they think is too dangerous. So there's a difference between having an aqueous solution and a chemical reaction, right? An aqueous solution, like salt water, for example, right? The salt is still salt, okay? Because if you were to evaporate all the water, all the hydrogen and all the interactions between water and the individual salt constituents, right? Sodium and the chloride, it still stays the same. It's still salt, right? You evaporate. In fact, there are people thinking that to help with the water crisis, apparently we're low on fresh water in the world. I didn't know that, but we have a scarcity of fresh water in the world. Um, Probably not in the United States, but in other countries. And a solution to that they're proposing is taking ocean water and evaporating off the salt, right? Sorry, evaporating the water off of ocean water and then distilling that water into another pot. Does that make sense? Right? Condensing the water somewhere else. Yes. Literally you take literally you take just a big bucket of ocean water. You can evaporate it off, right, and get all that water vapor and then bring it somewhere else, like pipe it somewhere else and let it condense into fresh water in another pot. So that's what people are thinking they're going to do, right? But the point of that story is that when you have salt water, salt is still in there. It's not changed, right? But here, I mean, we totally could have done this in class, but it was too dangerous, I guess. You don't see it, but usually there's bubbles coming off here that could like overflow, and then you could just die. It'd be a bad thing, right? But it'd be a bad thing. But here we have nickel, right? The metal nickel, and what happens here is that we drop it into hydrochloric acid, and not just any weak hydrochloric acid. We're talking about concentrated straight from the bottle hydrochloric acid, right? And that's the other thing too. Hydrochloric acid readily turns into hydrogen chloride gas, and if that went into your throat, that would be a bad idea, right? That actually happened once in lab. I had a student, and this was a class at Sam Houston called Advanced Integrated Lab. So it was the very last class you ever take as a chemistry major, and this kid took hydrochloric acid, straight hydrochloric acid, not even like diluted or anything, just straight up, hydrochloric acid. And we all know we're supposed to throw those kinds of things in waste, right? But he had a sink full of water, and he poured it into the water in the sink so it could go down the drain. And instantly, all this fog just came up, like fog of hydrogen chloride gas. And this idiot, I don't know why, he stayed there coughing, like trying, like choking on the hydrogen chloride gas. And I could hear him saying, "Doctor, doctor, no!" And I'm like, "Dude, why are you still standing there? Why would you stand in that smoke? You know? And so we ended up having to evacuate the entire lab because it filled up the room, and and we had to turn on the emergency vents to vent it all out into the atmosphere. So sorry about those birds that were on top of the smokestack that day. So I don't know if they survived that, but we survived it. So that's the important part, right? Anyway, so that's probably another reason why they didn't want us to do this experiment in here, because it would have filled up the room with hydrogen chloride gas. It would have been bad for everybody, right? But we're wearing masks. Maybe that would have helped. No, it wouldn't have. It probably would have just burned straight through the mask, honestly. So anyway, oh man, this same guy, so many stories. I used to have this blog back when blogs were like, super popular, called Tales of the Integrated Lab, and I'd tell stories of what happened in that lab. That's not even the worst story that happened in that lab. I'll tell you the next when we go over something that is that is relevant to this one story. I will tell you the story, but it's just crazy. All right, so we can take nickel, we'll throw it into some uh some hydrochloric acid, right? And eventually it all dissolves. Like you don't see any more nickel left, right? But is it really dissolving though? No, it's not dissolving. Actually, what happens is that you can remove all the hydrochloric acid, and after a while, now you have nickel chloride because you have converted the the nickel, right, to nickel chloride. This is a very simple reaction, right? Where we have a single replacement there, right? A single replacement reaction. The chlorine from the hydrogen chloride got put on the nickel, right? And so the what can get evolved from this is hydrogen gas, right? So you could actually use it to fuel your cars if you needed to, right? Those liquid fuel cell cars, that'd be cool, right? But you don't want to breathe in hydrogen gas. That's a bad idea because I think it's also flammable. But anyway, so yeah, you get nickel 2, right? And you also get hydrogen gas because it's a single replacement reaction. And so when you evaporate it all off, right? Evaporate off all the water, assuming that you've actually gotten rid of all of the hydrochloric acid, all that's left should be water. You evaporate it all off, you get this cool little green, you know, leprechaun-looking kind of substance called nickel chloride, nickel 2 chloride to be exact, right? Nickel 2 chloride. And actually, funny thing, when you look at a bottle of nickel 2 chloride, it's usually called nickel 2 hydrate chloride because there's 6 water molecules still left in there, right? So what happens is that they'll do this kind of thing and they'll evaporate off all the water, but not all the water goes away. It stays with it, right? And so it's not just nickel 2 chloride, it's actual nickel 2 chloride hexahydrate. You can also evaporate even more, like put it into a kiln and go up to like 3,000 degrees or something, and then that would remove all the water, and then you get nickel 2 anhydrous. So the word anhydrous means without water, right? And let me just tell you, it's a lot easier dissolving nickel 2 hexahydrate than it is to dissolve nickel 2 anhydrous. Why is that, do you think? Because like likes like, right? It's just like having a sponge that's dry and having a sponge that's wet. What's better at soaking up water? The wet sponge, because water likes water, right? Have you ever noticed that? I'm serious. Get yourself a dry sponge and try to soak up some water. Not going to work, right? You just let it sit there. Eventually, but if you pick up that water fast, make the sponge damp first, and then we'll pick up the water, right? It's the same thing in chemistry, right? When you have water already with the molecule, like this nickel 2 hexahydrate here, it's going to dissolve in water way better because like likes like, right? But if you just have nickel 2 anhydrous, you can sit there for a little while, stirring, stirring, and it's not going to go. Okay? So make sure you know that. Make sure you know that. All right, so make sure you know the difference between having an aqueous solution like salt water, right? And then a chemical reaction like nickel 2 chloride with hydrogen chloride, hydrochloric acid and nickel. Okay? All right. Next question. Whew. I feel like I'm talking a lot. Oh, wait, that's my job. That's my job. All right, let's see how people are answering. Is this one scanning for you, Daniel? I wonder why the last one didn't scan. That's weird. I'm going to turn you people into chemists if it's the last thing I do. Or at least, good chemists from Gen Chem 2. All right, everybody's responded? No? What happened? Has everybody responded? Oh, okay. Oh, I thought they're. Oh, Sean is back. That's why. Got it? Okay. So this is what I'm talking about right here, okay? So, this is what everybody said right here. And for some reason, we're split on what the answer is going to be, right? Now, I can let you talk about this, or I can go back to the slide that literally says this, right? And when I told you that exothermic processes are spontaneous, they readily happen, right? Spontaneous means they readily occur, they just happen, right? And it has a negative delta H, okay? So I literally said this 2 slides ago. So how is it possible that half of you got it wrong? Like, how is that possible, right? I expect everybody to get that one right when I like harp on it over and over again, okay? So the answer to this is, for the people that got it right, is yes, it is D, all of the above. And I didn't even mess up that question. Because an exothermic process is definitely spontaneous. What does spontaneous mean? It just happens, readily happens, right? Readily occurs, right? And they have negative enthalpies, right? What is an enthalpy? That's delta H, right? So, when I say that something's super important, you've got to remember that, okay? Or not remember it, but at least Okay, so let's see here. What's next? Oh, opposing processes. Okay, so the solution making process and crystallization process, right, are opposing processes, okay? So when we're talking about salt, we'll use salt again as our example, salt water, okay? The solute is what? What? No, the salt is the solute. What is the solvent? The water, because water is the universal solvent, not the universal solute, right? So the solute plus the solvent, when it dissolves, it becomes a solution, right? But you can go the other way too. You can totally go the other way. And it's that process I was talking about when we desalinate salt water to make water for like third world countries and stuff, right? What you're doing, you're just crystallizing all the salt out so you can get the water out of it, right? They're opposing processes, okay? When the rate of opposing process is equal, additional solute will not dissolve unless some crystallizes from the solution. This is called a saturated solution. So what that's saying is that you have some water, right? And you're adding salt to it, and you're just trying to see how much salt will get dissolved in there, and it becomes clear, right? And you just keep on going, right? Keep on going, and you get to this point where no more salt will dissolve, like just no more salt, okay? And that's called a saturation. That's called saturation, okay? So what that means, and also what does that mean, is that what it means is that some of the salt crystals that were already dissolved have to come back to being crystals for other salt crystals to dissolve. Does that make sense? So that's the point of saturation. But then there's an unsaturated solution, which is that process before you get to the saturated solution, right? Things are still dissolving. Crystals are still going into water, and you don't have to have any of the other salt molecules come back to being crystals for the salt water to keep on dissolving, right? So we have the saturated solution and the unsaturated solution, okay? So that's all based on this thing called solubility. Solubility is the maximum amount of solute that can dissolve in a given amount of solvent at a given temperature. Okay? At a given temperature. Saturated solutions have that amount of solute dissolved, right? A saturated solution will have the maximum amount of stuff in it that you can dissolve in it, okay? And then unsaturated solutions have any amount less than that. So just so you know, I've gone over this topic here now over 3 slides. That's probably important to know, right?
So, like when you hear about saturated and unsaturated fat,
That's completely different.
oh,
That is based on chemical structure. A unsaturated fat is one that has double bonds on it, right? A saturated fat is one that is completely hydrated with hydrogens on it. And we will actually talk about that later today, or maybe on Monday in class. So, but that is not the same thing. That's an organic chemistry thing, but we will talk about it. We will touch on it. Surprisingly, dun dun dun, there's one more thing. One more type of solution. That is called the supersaturated solution. And I actually have a little demo, something that they'll let me do because it's contained, right? A supersaturated solution, right, is a solvent that holds more than is normally possible at that temperature, right? These solutions are unstable. They can crystallize pretty much anytime you have a seed crystal, and these solutions are uncommon, okay? So generally what will happen is that you can heat up some water, right, to like boiling, and it will dissolve more salt than is actually normal, right? And if you let it cool down, if you don't touch it, it will stay in solution. But then if you touch it with your finger, what's going to happen? It's going to come out of solution because it's supersaturated. And I have an example of that. So my I was about to say my mom, but it's actually I was about to say my Marla. Marla's my girlfriend, right? A couple of you met her before. So she and I, well, she talked me into going to the Home and Garden show, okay? And of course, at a Home and Garden show, they're trying to sell you all kinds of crap, okay? All kinds of stuff. And I got suckered into buying one of these. This thing costs like $80, okay? And this is literally a saturated solution of sodium acetate. Actually, it's a supersaturated solution of sodium acetate, okay? It's a supersaturated solution of sodium acetate. It's got food coloring in it, so it's orange, right? But it's not supersaturated. And what happens is that there's a little tiny coin in there that pops. When you pop it, it causes all the sodium acetate inside to crystallize, right? That's that seeding the crystal part that we're talking about right here, right? Seeding the crystal, right? And when things come out of solution like that, a supersaturated solution, it gets really hot. And so what people use this for is a heating pad, right? So watch this. Everybody stop writing for a minute and watch this. And then I'll pass it around for you to touch because it gets really hot, right? So here's the coin right here, right? Does everybody see it? I'll pop it like this. See that? It's starting to form crystals, right? And now, pass it around. Feel it. You see how hot it's getting? Yes, exactly. Yes, you have to boil it to get it back to solution. You see how hot it is? So people use it as a heating pad. Yeah. So literally, I could have made this myself. Okay? I literally could have made that myself by boiling sodium acetate and water together until it became supersaturated, add a little food coloring to it, right, and put it into a Ziploc bag. But somehow she talked me into getting one of those that cost $80. Okay? So, and by the way, sodium acetate, you can get a freaking like 10 pounds of sodium acetate for like $10. And water is free, of course. But yeah, you see how that's a supersaturated solution. Okay? And all it took was one little snap of the coin, and it caused it to uh, become crystals again. Yeah. Yeah, it's really hot. And then someone else, I think it was it Savannah? Were you the one that said it? You're supposed to boil it to get it back down to get it back to liquid phase again. Oh my God, no, it takes a long time. Oh yeah, oh yeah. But yeah, that's literally a super saturated solution inside of a plastic bag that you could make at home with this company here called Wonder Packs, right? You're selling it for like $80, but you could make it at home, right? Buy yourself some sodium acetate, right? Like from a chemical store for $10, and then just dissolve it in water while it's boiling until it'll stop dissolving. Put it in your Ziploc bag, make sure it's sealed, and then just put a little coin in there and pop it, and it will become that. Well, it's any. It could be anything. It could be a piece of metal just popped in there. It's all that is a piece of metal. Any metal. It doesn't have to actually pop. It can just move. That one particularly pops, but it can just be anything that changes, anything that disturbs the crystals. Okay. And it's so funny because it says these are uncommon solutions, right? These are uncommon solutions, but freaking Wonder Packs is selling like a gazillion of these at the freaking home show, like all the time. Like, it really burns my bacon that they sell this stuff for like $80. Yeah, exactly. I know. And but people fall for that stuff, like me. I fell for it. That's probably why that's why I'm upset about it. It's because I fell for it. It's what happened there. Exactly, exactly. And they even so what they did to really hook me in was that they had these smaller ones too that you could just use as hand things. Yeah, pocket ones, and they were really super useful during the big freeze, you know, that we had in February because I didn't have any power, I didn't have any heat, I didn't have anything. So I'm so glad I got those, right? So that's how they hooked me. They hooked me with the freaking, and then also I like going to football games, and it gets super cold in football games, right? And having those hand warmers is a pain in the butt. And so having those keeps you warm for at least 30, 40 minutes. I know, right? Exactly. And then take it home and reuse it, right? Did someone just steal my $80 heating pack? Oh, sorry. I'm just kidding. Like literally, yeah, yeah. So you feel heat being released there, right? So what kind of process is that? Exothermic, right? What's the enthalpy? Negative, right? It's a spontaneous process, right? Because it just happened, right? You just watch the crystals flow out. Okay? Everybody got that now? That's what a supersaturated solution is. I bet you the reason why they let me use that in a demonstration is because I didn't ask. So, so, oh yeah, that's right. I got to delete that part. You're right. Good call. Thank you, Oceana. Thank you. All right, here we go. Next question. What is solubility? This is not. This is written correctly. I'm so glad I actually got to use that in class. All right. We got 7 responses. We're waiting for 3 more. Waiting for 3 more. 2 more now. One more, I think. Yes, one more. Yes, there we are. Okay, so thank the Lord. Thank the Almighty Lord that most of you got it right this time, right? Because the answer is in fact B. The solubility is the maximum amount of solute that something can hold, right? Maximum amount. Okay? Not the minimum amount. Who cares about the minimum amount, right? You keep on adding stuff to it anyway, right? Right? So thank you for getting that correctly. I really appreciate it. Okay? That's what Marla said. Marla said I should play the song like every day now. Yeah, yes. And then when a solvent holds more than what is normally possible, what is that called? Huh? When a solvent holds more solute than is possible, what is that called? Supersaturated, right? That's a thing you're holding in your lap right now, that supersaturated solution of sodium acetate. Okay? A solution has to be supersaturated for you to be able to get it to crystallize like that. Okay?
Is butter unsaturated or saturated?
So that's the same question that Stephanie just asked. Butter is saturated fat, but that doesn't mean the same thing, right? The saturated solution is not the same thing as talking about saturated fat. When you're talking about fats, it's based on the chemical formula, and for butter, it's saturated because all the carbons have hydrogens on them. But then you have unsaturated fats like oils that are room temperature and they're liquid, they have double bonds on them. That's the difference between those. So those are completely different things from this. But we will talk about that later on in life. Or I guess not today since class is almost over. But we'll talk about it on Monday. Yes, Monday. All right, so, oh my gosh, look at this. This whole slide here is dedicated to these three words. What do you think that means about those three words? They're important. Factors that affect solubility: the solute-solvent interaction, pressure, and mostly it's for gases when we talk about pressure, and then temperature. Because remember, I just said, how do you make the supersaturated solution of sodium acetate to make that $80 Wonder Packs piece of crap? You've got to heat up the water, right? You got to boil it. And then to get it to go back into solution to liquid again, you've got to boil it for like 10, 20 minutes, right, Savannah? Maybe longer, depending on how big the thing is. So factors, what? Sorry. Make it what? You can.
Like in a bed, like a really big bed.
You could. You could, but that would be a pain trying to get it back into solution.
Wait,
They-
so how long does it stay hot?
Like 30 minutes, maybe? Yeah.
And that's fun.
Because it runs out of energy. So you're going to lay on your back and it's like all hard, but you don't get any heat from it at all. And then you've got to take your entire mattress and throw it into a big pot of boiling water to get it back to normal again. And then you'll have to pop it again every 30 minutes. You have to do it again. So,
It'll be a water bed, but it'll get you to sleep. And then when you wake up, you just have to reset.
actually, studies have shown that you actually sleep better and fall asleep better when you're at colder temperatures. So we're talking like,
I mean, at school, y'all be keeping it cold in here.
yeah, exactly. It turns, I think it's like 69 degrees in here, 68 degrees in here. That's why I'm wearing a little sweater today. But that's the exact temperature you need to be at to fall asleep like almost instantly. So, yes. I've noticed that about you, that you fall asleep in here, but that's okay. It's all good. It's all good. Okay. All right. So this will be the last couple slides here, I think. Let me check. So remember what I said before? Like dissolves like, right? That's super important. That's like the phrase of this entire chapter. Like dissolves like, or like seeks like, or like likes like. All means the same thing. And what it means is that things that are similar to each other will dissolve each other. Okay? Like similar in polarity, similar in chemical structure, all those kinds of things. Okay? The reason why salt and water are so dissolvable with each other is because they're both super polar, right? Water is super negative on one side, positive on the other side. Salt is also super negative on one side because of the chloride, super positive on the other side because of sodium, right? So like likes like. All right, so, but that doesn't explain everything. The stronger the solute-solvent interaction, the greater the solubility of that solvent. That's what I was saying 2 or 3 slides ago, right? If the interactions of solute and solvent are stronger, then the interactions of solute and solvent, then you'll dissolve it, right? Okay, I said that a couple of slides ago. And then gases in the table exhibit only dispersion forces. The larger the gas, the more soluble it will be in water, right? Okay, let me catch my breath. Okay, so we have nitrogen gas right here. It's the smallest of these four, right? And it's actually not that soluble in water. You can actually bubble nitrogen gas through water, right? Same thing with oxygen. But the oxygen does dissolve in water. That's how fish breathe, right? Fish breathe through their gills. And so their gills actually filter out dissolved oxygen in the water, right? But still, oxygen is not super dissolvable in water. But the bigger it gets, like argon and krypton here, the more dissolvable it is in water, right? But even then, you see that these are like to the -3, right? So they're still really super small numbers. We're not talking about like salt that's like super dissolved in water, and it's like a whole number, right? Those are all decimal points. All right. So yes. Next question. Which is not a factor that affects solubility? All right, solubility factors. We've got everybody responded. Oh, thank the Lord again. Let's see here. Thank the Lord again. Yes, the answer is true. Not true. The answer is D, right? D is the only one that's not a factor. That's volume, right? The only three factors I had for you were what? Solvent, pressure, and temperature. Okay? All right. Oh, we still got 5 minutes, so we're gonna finish this up right here. Who put the wrong answer? I'm just kidding. I don't want to know. I just don't want to even know. Don't even want to know. I can look it up later because I know who answers what. So I'll look it up later. We'll have a very stern talking to about it later. Okay. All right. Here we go. This is what I'm talking about. Fats. Here, right here. Okay. So organic molecules and water. Organic molecules generally are nonpolar, right? Because they're hydrocarbons, carbons and hydrogens, stuff like that, right? So polar organic molecules will dissolve in water better than nonpolar organic molecules. Hydrogen bonding increases solubility, but when you have just carbons and hydrogens, there's no hydrogen bonding. So you can't dissolve it, right? With anything that's just carbon and hydrogens, right? Because these bonds are not very polar. So what I want you to look at here is ethanol, right? Ethanol has hydrogen bonding because there's an oxygen there with a hydrogen. That is a electronegative to hydrogen, right? Which means it can do what? Hydrogen bonding. And look what happens in water. Easily, right? Easily do that, okay? This here, right here, this is just a hexane with a whole bunch of OHs on it, which is actually interesting because that's like a hexose, like a sugar, right? It does have OHs on it, right? So it can do hydrogen bonding, but it has a lot more carbons on it too, and hydrogens on it too. Ever notice that the sugar is a lot harder to dissolve in water than salt is? That's why, right? That's why. But then we have this up here. Oh, look, I was right. It's a sugar. It's glucose. I said hexose, but that means the same thing, by the way, right? I didn't even know that was. Man, my memory's awesome, right? Anyway, and then we have cyclohexane here, and cyclohexane here is all just carbons and hydrogens, right? And that's not dissolvable in water at all. That's not soluble in water at all. Go ahead. What lines? Oh, these lines. So in organic chemistry, when we draw a three-dimensional molecule, when you have a dark line coming like that, those dark lines mean it's coming out at you, right? Because it's a three-dimensional molecule. When it's like this, where it's just a regular line, it means it's flat with the board, right? And then you'll see some that have dashed lines. That means it's going towards the back of the board, okay? That's not something you're going to get tested on, by the way.
So the OH groups enhance the accuracy of solubility, meaning that's why they cannot easily dissolve in water.
Right.
Sugar.
Sugar. Yes, yes. Because glucose is a sugar.
Because of their affinity to OH.
Right, because the sugar has OHs, right? So it can do some hydrogen bonding, right? And that's why it can dissolve in water. But it still has a whole bunch of other carbons there too. And so that's why it's not as dissolvable in water as something, say, like salt is, right? Which you see that when we make tea, right? How many times have you made tea and you forgot to add the sugar in before while it was still hot, and you added it in afterwards, and you're stirring, and the sugar is still at the bottom, right? But while it's hot, you can dissolve the salt. Ooh, that's salt in tea, nasty. Sugar, well, you can dissolve the sugar in tea easily if you do it when it's still hot. Because why? Heat is a factor that does what? Affects solubility, right? I have never put salt in coffee before. Okay, so I think we're going to go ahead and end it there because the next thing is about liquid stuff, and we'll finish that next time. Okay? We'll end it there.